Hi, welcome to Mathematics of Chemistry, Part 5. My name is Dr. English. Today we're going to be talking about precision, accuracy, and percent error. Specifically, we're going to talk about what is the difference between precision and accuracy, what is percent error and how do we use it in chemistry, calculating percent error, a little bit of practice associated with that, and then finally density and a little bit of practice. So what is the difference between precision and accuracy? Precision is how closely individual measurements agree with one another. So if I gave you 3 measurements, I could say, well, how precise are they? In other words, how close in measurement are they to one another? Compare that to accuracy, and that's how closely individual measurements agree with an accepted value. So with accuracy, you're comparing your measurements to a published value that's out there, whether it's a reliable source on the internet or your textbook. So accuracy always relates back to an accepted value. Precision is how values compare to one another. One way of showing this as an example is through the use of a dartboard. If our accepted value that we're trying to achieve is a bullseye, then this first example that we see right here demonstrates both good accuracy and good precision. It's good accuracy because all the darts are hitting our bullseye in the middle. It's good precision because all the darts are going to the same place. In other words, this person's a pretty good dart player. In this next example that we see right here, we see poor accuracy because none of the darts are basically hitting our accepted value of the bullseye, but it's pretty precise. So when we look at this particular diagram, they're very precise because they're all hitting the same spot, but they're not very accurate because they're not hitting the bullseye. And then this final example right here is showing poor accuracy, poor precision, and they probably need some more practice. The darts are all over the place on the dartboard and they're not hitting the bullseye. In general, this summarizes the difference between precision and accuracy. Now let's talk about percent error, and this formula is listed for you on Table T. When you do an experiment in which a known value is to be found, in other words, you're finding a value, that's something that you're doing, you will find that you probably did not determine the exact value. The amount by which you missed the accepted answer is expressed as percent error. The percent error of a given value is the comparison of that value with the number that is accepted as the true value. To find the percent error, use the following relationship, where we have percent error is equal to the measured value, that is what you are doing, you are measuring the value in lab, minus the accepted value, which this will be a given, divided by the accepted value, which again is given, times 100. So let's look at an example. The accepted volume of 1 mole of any gas at STP is 22.4 liters. If a student finds the volume of 1 mole of gas at STP to be 21.2 liters, the percent error is, all right, so we have our percent error formula. So percent error equals 21.2 liters. This is the student's measured value. This is the student minus 22.4 liters. This is our accepted value. So accepted, that says accepted, divided by the accepted value of 22.4 liters times 100. If we work that out, we'll get negative 5.36%. Now, don't freak out about the negative. The negative value for the percent error above simply means that the measured value is less than the accepted value by 5.36%. So again, if you get a negative percent error, it's not a bad thing. It means that your value was just a little bit below the accepted value. Let's do another practice. A student determined that the melting point of an unknown solid to be 55.2 degrees Celsius. The accepted value is 56.8 degrees Celsius. What is the percent error of this student's determination? So here we have our percent error formula right here, which is percent error equals measured value minus accepted value divided by the accepted value times 100. Let's go ahead and plug our values in. So the measured value here is 55.2 degrees Celsius minus the accepted value, and the accepted value is 56.8 degrees Celsius. So 56.8 degrees Celsius. We're going to divide that by 56.8 degrees Celsius, and then we're going to multiply it by 100. When we do that, we're going to get negative 2.8169%. Now, when I think about significant figures here in my answer, I go back to my original problem. I say, well, 55.2 is going to have 3 significant figures. 56.8 is going to have 3 significant figures. Therefore, when I look at my final answer here, I'm going to round this to negative 2.82%, which means that my value is just a little bit below the accepted value. So in the end, again, you want to write out your formula, plug in the numbers that are given to you, solve using the correct math, and then think about significant figures at the end and make sure your answer is to the correct number of significant figures. Let's talk about density. Now remember, the density formula is density is equal to mass over the volume. Please, please, please don't put the little triangle on your paper. I know you might have learned the little triangle, which has got, I don't even know what the little triangle is, but it's something that you might have learned in middle school, but really at this level, not appropriate. Not appropriate. Use the formula, use the math that you know. Density is equal to mass over volume, and the volume can either be in centimeters cubed or milliliters or liters. It really depends on the situation. So density is the ratio of the mass of an object to its volume. So let's look at an example. A bar of silver has a mass of 68.0 grams and a volume of 6.48 centimeters cubed. What is the density of the silver? So density is going to equal mass over volume. I'm going to write my mass on top, 68.0 grams. I'm going to divide that by the given volume of 6.48 centimeters cubed. And when I work this out in my calculator, it's 10.49 grams per centimeters cubed. But again, I take a moment and say, well, here we have 3 significant figures, here we have 3 significant figures, therefore my answer should have 3 significant figures. So when I round this to the appropriate number of significant figures, it should be 10.5 grams per centimeters cubed. And the last question is, how does this compare to the value on reference table S of your reference table? Well, it turns out it's exactly the same thing. So remember, on table S, one of the columns is density, so you want to make sure that you look at that and you remind yourself that the density values are there. Let's look at one more practice problem. The density of gold is 19.3 grams per centimeters cubed. What is the mass of 11.3 centimeters cubed of gold? All right, so I'm going to write out my formula first. Density is equal to mass over volume. They're giving me density, so 19.3 grams per centimeters cubed equals, we're looking for mass, so that's my x. I'm going to put that over my volume, which is 11.3 centimeters cubed. I'm going to cross multiply here, and when I cross multiply and I solve for the mass here is going to equal 218 grams. 218 grams. And that works out nicely for us because this has 3 significant figures and this has 3 significant figures. So what did we learn in this brief tutorial? We looked at the difference between precision and accuracy. We talked about percent error. We did a calculation with percent error. We did a little bit of practice. And then finally we wrapped it up with some density at the end. Need more help? Feel free to contact me. Have a great day.